Happy Monday, everybody. My name is Robert Larrabee, and I'm coming from Swansea University. Thank you for the very lovely introduction, by the way. So the title of this talk is called Flow as You've Never Seen It Before, or Go with the Flow Visualization. There are two titles for this talk. So has anybody ever heard of flow visualization before in this audience? Yeah? So flow visualization is useful to gain some insight into flow data. So flow data describes fluid motion. So fluid motion is vector data, and all the vectors have a direction and magnitude. And there's a community, an engineering community, very strong in the UK, called the computational fluid dynamics community, generating massive amounts of CFD simulation data. And what they're discovering is that the greater the data sets are that they're generating, the more difficult it is to analyze them, to present them, to explore them, and to gain insight from the data. So flow visualization is attempting to bridge that gap to enable using computer graphics so that engineers can gain insight into their computational fluid dynamics data. And this is just a taster talk. It doesn't go into any technical details. It's meant to just show what's possible in flow visualization, some of the things that we've worked on, because we're always trying to come up with new ideas on innovative flow visualization. And if there are any questions and comments during the talk, feel free to just interrupt. So this is just a brief introduction to who I was, but the moderator already went through that, so I'm going to skip that slide. These are two examples of flow visualization. So this is visualizing flow, just the magnitude of the flow, color map to color. This is the most common way to visualize flow. This is a texture-based flow visualization, which shows the orientation of the flow only without the magnitude. So the idea is, can we combine the magnitude and the orientation information into one image or a series of images or one visualization? One of the classic techniques for flow visualization is using streamlines. So streamlines are curves that are everywhere tangent to the vector field. And CFD engineers spend a lot of time positioning the curves manually with the seeding rig. So we tried to come up with an algorithm to help them do that automatically. So instead of trying to position a rig manually, we present an algorithm that does it automatically, right? And this has a special property in that all the streamlines are approximately evenly spaced to one another, right? So the idea behind evenly spaced streamlines, or nearly evenly spaced streamlines, is you get complete coverage of the flow. And this is showing the evenly spaced streamlined algorithm in action. So it should be quick, right? It should be interactive. It should give coverage of the flow. And this particular version of the algorithm is adapted for surfaces. So these are all surfaces that you find in computational fluid dynamics simulations that are simulating the flow through automobile engine parts, different automobile engine parts. This is the user zooming in on a specific part, and it's just showing that it's an image-based algorithm, so there's an edge detection aspect in there that prevents streamlines from crossing over edges. We can animate the streamlines, for example. Right, this shows a real-time animation of the streamlines, and that gives us the downstream direction of the flow. We can rotate, zoom in, and pan. We can add artistic effects to the streamlines, tapering. That means making the endpoints or the ends of the curves very thin, sort of like an artist. This is also showing the underlying CFD mesh. So the underlying CFD mesh is very complicated. It's adaptive resolution, it's unstructured, and it's high resolution. This is the user interactively adjusting the spacing parameter between the streamlines so they can control the density of the visualization. This is showing the different kinds of seed points. So we categorize the streamline seed points into different categories, and that's showing a visualization of those seed points. Since it's an image-based algorithm, all the streamlines are evenly spaced, but we can add something called perspective foreshortening, which is making the streamlines closer together as a function of distance from the camera. Right, so here they're all the same. They're all the same, and it doesn't matter how close they are to the camera. But in this version, the further we are away from the camera, the closer the streamlines are together. Anybody know what that is? That object is that we're looking at? It's a cooling jacket. It's one of the automobile. It's the part of your engine that keeps it from overheating. Okay, so that's the first example. It's an automatic streamline seeding algorithm. There are also these objects called stream surfaces. So streamlines are curves that are everywhere tangent to the vector field. Well, stream surfaces are surfaces that are everywhere tangent to the vector field. They're the next higher dimensional equivalent of streamlines. And we worked on algorithms for fast construction of stream surfaces. So they separate the regions of the flow into different behaviors, right? They produce imagery that's not as complicated as lots of streamlines in 3D space, right? These are stream surfaces, right? Surfaces that are everywhere tangent to the flow. They offer an enhanced perception because they have well-defined normal vectors, so we can apply shading in a natural way, which is not so easy with streamlines, right? And surfaces provide more rendering options. However, stream surfaces are more difficult to implement and construct than just streamlines. So that's one of the disadvantages. Occlusion is a challenge, and placement is a challenge. So let's see what the stream surfaces look like when they're being used to visualize flow. So we worked on an algorithm that tried to simplify the construction of stream surfaces so it wouldn't be so complicated as it usually is. So this is a surface that's everywhere tangent to the flow. And that's the user interactively adjusting the integration time of the surface, right, or the length of the surface from the beginning to the end. And this is a helical flow. Also, it's a simulation of a tornado. So this is a simulation, a CFD simulation of Hurricane Isabel. And this shows the quad mesh that the surface is composed of. And the quad mesh has different characteristics. Each quad has divergent, convergent, and laminar characteristics. Here we can just apply different rendering options to the surface. So we can add arrows that show the downstream direction. We can vary the opacity of the surface, right? We can put in holes, see-through, so we can see through the arrows, or we can make the surface mostly transparent. The point is, it's very easy to apply texture mapping to these surfaces and then gain different characteristics or different visualization properties with the texture mapping. So that's the user interactively adjusting the texture mapping parameters to show different ways to render the surface. And these are animated stream arrows, so they're arrows that go in the downstream direction of the flow to show its orientation and its direction. And it can be done in real time since it's a texture mapping, using the texture mapping hardware. So we can animate the surface in real time and update the texture properties. So you might have noticed so far we've only looked at examples from steady state flow. So that's flow that doesn't change over time. So this next example looks at unsteady flow or time-dependent flow, which changes over time, right? And we developed an algorithm for constructing streak surfaces. So streak surfaces are a surface that's inside of unsteady flow, three-dimensional flow. I can't say that it's always tangent to the unsteady flow field though. It's the equivalent of dropping a massless sheet into the flow and just watching it move. That's what it's essentially the equivalent of. And it's analogous to experimental flow visualization, which uses dye. So experimental flow visualization engineers drop color into the fluid and watch what happens to the color as it gets infected by the flow. So this is what streak surfaces look like, and you'll notice the difference you'll notice the difference very quickly from the stream surfaces and the streak surfaces. Now, the Swansea University was actually the first place to develop a streak surface construction algorithm. And so this is one of the, this was a problem that remained unsolved for 20 or 30 years because the surface is very complicated. We have to update each vertex of the surface at every frame, at every time step. It becomes computationally expensive. So this is the first interactive streak surface construction algorithm. And this is flow past a square cylinder, so the flow is moving in this direction. The user has chosen a seeding rake to inject the surface, so to speak. And this is how the surface gets deformed over time. And it shows the characteristics of the flow. What happens to the flow as it passes over time. And you can see that the evolution of the surface is complicated, right? It has a complex geometry and it has a complex topology as well, right? It breaks apart into different pieces. We worked on this one for a long time, actually. It took it over a year to develop this algorithm. But the results are quite interesting. So this also runs at interactive frame rates. So this runs at about 5 frames a second. That's one of the goals, is to generate flow visualization algorithms that are interactive and can run at fast frame rates. This shows the same simulation data, but the orientation of the rake is rotated by 90 degrees, right? So it hits the square cylinder, wraps around it, and then carries on. And it also shows it demonstrates what happens to the topology of the surface as it hits an object, right? That it can split apart and then wrap around the object and then carry on. And here we can see classic vortex shedding. This is one of the sort of the classic flow features of flow past cylinders and flow past blocks. Right? And this shows that the surface can tear apart and change its topology to show the characteristic vortex shedding. Has anybody seen this before? Probably not. By the way, the color is mapped to velocity magnitude in this case. So this is high velocity magnitude, fast flow, and this is slow flow. So this is the highest velocity, and the slowest velocity is right behind the cylinder. Okay. Okay, we also worked on stream surface placements, but since we've already seen stream surfaces, I thought, and we're running out of time, I thought it might be more fun to look at texture-based flow visualization. So this is a different style of visualization. It doesn't use discrete objects like streamlines, stream surfaces, or streak surfaces. It uses textures that look like this. And it provides complete coverage of the flow, and it avoids this so-called seeding problem. So let's see what it looks like when we visualize flow with textures. This is a video that shows lots of different techniques in rapid succession, actually, applied to CFD simulation data. So this is the texture-based flow base applied to a slice through an engine simulation data. That's the same data, but with streamlines visualizing the flow. We're trying to capture that swirl motion that's characteristic of this particular engine simulation. Right? That's the texture-based flow visualization again. So it looks much different than the streamlines and the stream surfaces. And again, we can compute those textures in real time because we're using the GPU. We can run the algorithm at more than 20 frames a second. We can change the input texture so it resembles something that looks like dye, which is what we just saw. These are animated streamlines. This is a noise-like texture that shows the flow at the surface of the cylinder. The user rotating the cylinder. It's also showing that the same techniques can be extended to surfaces, not just slices, two-dimensional slices. So this is another simulation. So this is the surface of we can see a vortex in the bottom left-hand corner there. That's the same data, but the input texture is being changed to simulate the convection of dye. Right? These are so-called timelines. So we can simulate the timelines with the same technique. These are the classical three-dimensional streamlines being seeded with a seeding plane manually. Now they're animated to show the downstream direction. There's the seeding plane again. There are two seeding planes here with animated streamlines emanating from the seeding planes. And this is a combination of different techniques. So that's an iso surface, those are 3D streamlines, and then we add texture injection to this iso surface. This is another combination of several techniques, a pressure iso surface, 3D streamlines, and texture-based flow visualization as context. Okay, how much time do I have? 1 minute. So just as for the last minute, I'll just mention we did work also on a stream surface seeding algorithm. And it's usually stream surfaces are seeded manually with a rake. But we worked on an algorithm to do it automatically or semi-automatically because doing it manually is very difficult. It's very time-consuming. It's very laborious, and it's full of can lead to errors. So that's just a tiny 30-second preview of what it looks like to see automatically seeded stream surfaces. Okay, thank you for your attention, and I'm happy to answer any questions. Just as a little note, all those videos are on my webpage, and they're all on YouTube as well, if you want to check out any of those again.
Okay. Any questions? Not, I would have a quick question. So, what would it be also be possible to have those visualizations really in 3D space on stereoscopic or other 3D displays? What's your opinion on that?
Definitely, it's definitely possible. It's not something we work on. That's more in the virtual reality sort of arena. To have like a cave or a head-mounted display, but I've definitely seen these techniques. There's no reason why they can't be applied to 3D environments.
Okay, then
I have
yes,
another
please.
question. I'm not know about your scope, but this scope is a computer vision or graphics, computer graphics.
I would say it's not computer graphics or computer vision. It's data visualization.
Or with physics.
Oh, the simulation data is engineering, so it's computational fluid dynamics. So we take the computational fluid dynamics data and we apply the flow visualization techniques to that data. Yep. So there's at least 10,000 people just full-time generating CFD data on a full-time basis, just in the UK. It's a huge field, but they're all hiding in their closets. They don't talk to normal people for some reason. I don't know why.
Okay, well,
Thanks.
again, and I would like to hand over the speaker certificate to you.
Oh,
Well,
thanks.
thanks a lot for your
Thank you
very
very much.
appealing presentation.
Thanks.
Thank you very
Thanks a
much. So the next presentation will be given by Leonardo Sartre. He's an adjunct professor at Federal University of Santa Catarina in Florianópolis, Brazil, and he received his bachelor's degree in mathematics and scientific computing in 2008 and the master of science and doctor of science degree. The next speaker is Robert S. Laramie. He received a bachelor degree in physics cum laude from the University of Massachusetts, Amherst, and a master's degree in computer science from the University of New Hampshire, Durham, and he was awarded the PhD degree from Vienna University of Technology in Austria. There he was also a researcher at the VIRIS Research Center and a software engineer at ABL, an Austrian company. And currently he is an associate professor in data visualization at Swansea University in Wales. His research interests are in the areas of big data visualization, visual analytics, and human-computer interaction. He has published more than 100 peer-reviewed papers in scientific conferences and journals, and has served as conference chair at Eurovis 2014, which is the premier conference on data visualization in Europe. So just for information for all the following speakers, I'll give you something 25 minutes are left, and then once again for 20 minutes orientation.